Here are some water molecules. They have specially oriented magnets so that the hydrogens can donate a hydrogen bond by sticking to oxygen, and the oxygen can accept a hydrogen bond by sticking to hydrogen. So they're specially oriented that way. Now, if you have something nonpolar, this is represented by something with no magnets inside. It has no attraction to the hydrogen bonding water because this, of course, cannot do hydrogen bonds. So if you have a couple of these mixed in with the water wants to do hydrogen bonds with itself. You could feel that every time you break a hydrogen bond, you have to apply some force with your fingers. That's true at room temperature in a cup of water also. Breaking hydrogen bonds requires the use of energy, which is the thermal energy that's available at room temperature. But now making hydrogen bonds returns that energy to the environment, so some energy is released when some heat energy is actually released when hydrogen bonds are formed. So hydrogen bonds are constantly being broken and formed at room temperature or at any temperature where there's liquid water. Broken and formed, but you see, every time the hydrogen bonds are prevented, let's say by a nonpolar thing. So no hydrogen bond can be made here by the two hydrogens because it is up against this nonpolar thing. No hydrogen bonding is available there because the nonpolar thing has no partial plus or partial negative, that sort of thing. So this water molecule is paying an energy penalty on its hydrogens because it doesn't have the opportunity to release energy by forming a hydrogen bond. So with all of these attractions at play in water, in liquid water, and all these hydrogen bonds being made and broken in liquid water, just as a result of the random Brownian motion of the water molecules, the nonpolar things will end up getting pushed together. Because if you have this one nonpolar thing, let's say it's surrounded by 5 water molecules, and this one is surrounded by 5 water molecules. See, that's 10 water molecules paying the energy penalty for not making hydrogen bonds on on one face of the molecule. So to reduce that energy penalty, just with the random motion from the thermal energy available at room temperature or whatever temperature this liquid water is at, just from the random motion, eventually a situation will arise where these two are sticking together. And when you surround two things stuck together with water molecules, notice that this surface has no water molecules. This surface has no water molecules. So we, instead of using 10 water molecules to surround this, you would maybe use 7, 6, some lower number. In other words, excuse me, the surface area of this plus the surface area of this is greater than the surface area of this one clump. So this, just from the random motion of water molecules using the thermal energy available in the ambient condition, this is what's going to happen, because from here, this is going to represent a lower energy situation than here. Why? Because here you have more water molecules giving and receiving hydrogen bonds, releasing energy. But here you have fewer water molecules giving and releasing hydrogen bonds because more water molecules are up against the surfaces of these molecules which are not playing. They are not playing the hydrogen bonding game. So that is why the nonpolar parts of proteins stick together, and that in water, and that is why tiny oil droplets in a cup of soup can tend to form larger and more easily seen oil droplets over time. That's why this happens. This is the hydrophobic effect. I took a microbiology class over at Cal State LA a couple decades ago, and the first week of the course, the professor was incorrectly telling us that nonpolar things in a cell stick together because of the nonpolar attraction called London dispersion forces, called by some textbooks just as van der Waals forces. But see, sure, London dispersion forces are a real thing, and they are significant, especially when the molecule is large, but compared to the hydrogen bonding of several hundred water molecules, London dispersion forces are negligible. Like, this guy wouldn't even know that this guy exists if there were a whole bunch of water molecules in between them, because the strength of a hydrogen bond is several times stronger than the strength of any London dispersion forces. Okay, so it is not the case that dispersion forces cause nonpolar things to stick together in water. Not the case at all. It's the hydrogen bonding of water that causes nonpolar things to get pushed together by water, which just by its random motion is making and breaking hydrogen bonds all day long, you know? And breaking hydrogen bonds costs energy, making hydrogen bonds releases energy, so eventually you end up with a low energy situation where as few as possible hydrogen bonds are being robbed, and as many as possible hydrogen bonds are being exchanged, right, by water molecules with other water molecules. This is just like having a skateboard at the top of a hill. If the skateboard is at the top of the hill, eventually, like next week, next year, you're going to find that skateboard not at the top of the hill anymore, because the top of the hill is a high energy situation. At the drop of a hat, like maybe a small tremor or gust of wind or something, at the drop of a hat, that skateboard is going to roll down the hill. Eventually, that's going to happen, and that is the hydrophobic effect. That is the reason why nonpolar things stick together. Now, I think it's cool for students to feel the strength of hydrogen bonds modeled by these magnetic attractions, and then to feel this lack of attraction modeled by a lack of magnets, right? And then I've also got this nice salt crystal model here with chloride ions and sodium ions, and these are specially prepared so that the sodium ions, the positive ions, stick to the partial negative side of the water molecules, and they do not stick so well to the partial positive side of the water molecule. So you can demonstrate, or you could have kids model the solvation of an ionic compound by water pretty accurately. You can't go wrong. Like, there is no way to get the wrong answer. If you just surround the sodium ion with water, you have to. The only way to make the water molecules stay there. I'm having trouble because I'm only using one hand. But if you want the water molecules to stay there, you have to give it the proper orientation, meaning the red side sticks to the blue. But if you do it with the chloride ion, that's not the case. Chloride ion attracts the white side. You see that? Just like that. So if you want to solvate this anion, you have to use the partial positive of the water molecule. And I think this is a useful way to show why ionic compounds such as salt get dissolved in water. Now, could water dissolve these guys? Well, you could see there's no attraction. So if there's no attraction, if you have a clump of these guys, nothing's going to happen. Water is not going to be able to separate these guys out of the clump. However, with these guys, the water molecules, you could feel the attraction here. Not like that, like that. Yeah, you could feel the strong attraction. Whew, that's pretty tough. And it's not that hard to conclude that the water molecule would easily be able to get in there, and separate these guys off of their crystal, and eventually forming this nice solvation complex. All right, so that is the water molecules kit. I've got these cheaper kit here of water molecules. Now this is less useful because it doesn't represent water as H2O, it just represents water as a ball. Each of these balls is supposed to represent one water molecule. The point of this is to model transpiration, how plant transpiration assists the plant in bringing the water up from the roots. Saw this on a educational computer animated TV show. I think I lost a magnet. Oh, there it is. But let's say this is the leaf. So as water molecules get released from the leaf. So why would the leaf want to release water molecules? It's because releasing, let's say, one water molecule would pull up a line of water molecules that are all attracted by hydrogen bonds. And if you just release this to the air just by diffusion, then so when this guy leaves, he pulls everyone else with him. This guy, because transpiration is a change of phase from liquid to gas, this guy just leaves by himself, but this whole line of water molecules got pulled, and then the next guy leaves, it pulls the whole line again. So this helps with the capillary action, the capillary action of bringing water up from the roots into the leaves, especially if the plant is very tall. These balls are meant for that concept. I'm not sure when you're going to get to that concept, but these balls are just easier to use than the full water molecule when you're trying to demonstrate transpiration and how it helps with the movement of water molecules up against gravity. Thank you. Bye.